All right, in this section, we're going to take a look at the concept of reduction of order. All right, so let's go and take a look at a second order homogeneous ODE, something that looks like this. You have some coefficient function times the second derivative of y plus some other coefficient function of x times y prime plus some other coefficient function times y equals to 0. So it's second order and homogeneous. This is equal to 0 here. Okay, so if you have this kind of problem, you know that the general solution will be the linear combination of some fundamental set, as we saw in the last section. Here, the general solution will be the linear combination of a fundamental solution set. That solution set will have two elements in it because, again, this is a second order ODE, second order linear ODE. So here we have two elements. Now, one thing we remember about the fundamental solution set, in fact, probably the most important thing, other than there being two of them for a second order problem, is that these must be linearly independent. Since y1 and y2 are linearly independent, then that means that they cannot be multiples of each other. You can't have this one be double that one, or you can't have that one be -5 times that one, because if that were the case, we could easily multiply that by the inverse of that coefficient and be done, right? If this is double that one, I could just say, okay, go ahead and multiply this by -2, and then when they combine, you get 0. So not linearly independent. Okay, so they're not multiples of each other. Okay, but if they're not multiples of each other, then if I were to divide them, I should get something that's not a constant. Right? If this was double this one, dividing them would give me 2, or 1/2, depending on which way I divided. But if they're not just multiples of each other, then dividing one into the other, y2 over y1, should give me some function, I'll call it u, and that function is not constant, so I'll call it u of x to highlight the fact that it actually is a variable function here. So, and in fact, let's highlight it even more, not constant. Okay, well, if that's the case, then I could always take y1 and multiply it to the other side, and this would give me that y2, the second solution in the fundamental set, would equal to the first solution times some function which we can call u. So here that's u, and I'm going to leave off the u of x part, but it is a function of x, keep that in mind. So u times y1. This is the basis of what we call reduction of order. All right? So here's how we proceed. Let's take our initial problem here. And in fact, let me just write it down again. I have a sub 2x times y double prime plus a sub 1x times y prime plus a sub 0x y equals 0. Again, homogeneous. And now we're simply going to substitute our result from here. Now, before we do that, we're going to take one little step here to simplify this into a way that's going to make the actual substitution a little more manageable, a little more palatable. What I'm going to do here, and this is not strictly necessary, but we're going to do this kind of as a, what do you call it? I guess just kind of as a standard. That's how we're going to proceed through any problem that looks like this. We're going to begin by dividing everything by this lead coefficient function. This is not strictly necessary. However, doing so makes this just y double prime, and it makes these still functions of x. A function of x divided by a function of x is still a function of x. Of course, here 0 divided by anything is, well, still 0. So this doesn't change much of anything. However, this is now gone, giving us y double prime. And since this is a function of x, you say, well, it's actually the quotient of two functions. Yeah, but when you divide two functions, you just get another function. So here, we call this p of x, or whatever letter you like, but we're going to stick with p. Y prime Same thing with this. We're going to call this q of x, y. And of course, dividing 0 by anything else is still 0. Okay? So this is what we're going to call the standard form. And this p and this q will, we're going to keep using this notation throughout the chapter. So this is our standard form. And although not strictly necessary, it is going to clean things up a little bit when we do it with this process. So standard form of a second degree homogeneous linear ODE. Okay. All right, so in this statement up here, we establish a relationship between the two solutions. Even though they're not linear combinations of each other, even though they're not, well, that's true, but even though they're not multiples of each other, there's still a relationship between them. Okay? We're going to exploit this relationship to find one from the other. All right, so here we go. Suppose that you know one of these two solutions. And to make it easier, I want to stick with y1. All right? So here, suppose y1 is known. All right, you figured it out somehow. We'll talk about how that is in later sections. But somehow you figured this out. Okay, well, it turns out you can actually use that one you know to figure out this other one. All right, so we're going to go ahead and substitute y2 is equal to u times y1. Now, you still don't know what u is, but it is related. This does relate y2 to y1. All right, so let's go ahead and find our necessary components. After all, we do need derivatives. Whatever we're calling our solutions, we need their derivatives. Okay, so y2 prime, well, that's going to be just the derivative of this stuff right here. That's going to equal to uy1 prime. Right? The derivative of this is the derivative of that. But this is a product. So I can use the product rule. It's going to be the derivative of the first part times the second, plus, leave the first part alone, times the derivative of the second. Just like that. And we can do the second derivative, y2 double prime. Well, that's just going to be the derivative of this stuff here. Right? So that's going to be u prime y1 plus uy1 prime prime. It's the derivative of this previous derivative. But now each of these uses the product rule. So here we go. That's going to be the derivative of the first one. That's u prime prime. Okay, so double prime. Times the second. Plus, now leave the first one alone, times the derivative of the second. y1 prime. And then same thing over here. I'm going to take u prime times y1 prime. And then leave the first one alone, and then take the derivative of the second one. So that's y1 double prime. Just the product rule. Notice right here, these are like terms, so I can combine those, and I get u double prime y1 plus 2u prime y1 prime plus uy1 double prime. I just combine those two as like terms. So now we can take these and, well, plug them in. So our standard form becomes, and then we just plug these in. So here's my y double prime, so I should plug that in first. I've got u double prime, y1, plus 2u prime y1 prime, plus uy1 double prime, plus, and then I've got p times y prime. Okay, well, p is gonna distribute to both of those. So I'm gonna say that's plus p times u prime y1, plus p times uy1 prime. P times uy1 prime, like that. And then finally I've got q times y, but again, our y is uy1. Okay, so it's going to be plus q uy1 is equal to 0. Okay? So basically what we've done is we've said, well, we know y2 is going to be a solution, so we could plug it in there, there, and there. But y2 is equal to this stuff, so we'll plug in this stuff there, there, and there, which is what we get here, here, and here. Okay. Now, this does look fairly complicated. However, there is something hidden among these terms. In fact, something very familiar. It's our original problem. Look right here. I've got uy1 double prime plus puyy1 prime plus quyy1. You say, yeah, so Well, look what happens when I rewrite this. All three of these have a common factor of u. In fact, they're the only ones that have u. The rest are u prime or u double prime. So here I'm going to factor out a u, and I'm left with y1 double prime plus, again, I'm factoring out my u, so I've got py1 prime, plus, factoring out my u, I've got qy1, like that. And then everything else, I'm just going to go ahead and bring it down. Oh, let's see. I guess I'll write this one next here. So I've got u double prime y1 plus, and then right here, both of these have a u prime. So I'm going to group those together as well. All right, this one here and this one here. And since they both have a u prime, I guess I can factor that out. So I've got u prime times 2y1 prime. And over here I've got p, factoring out my u prime, leaves me just y1 equals 0. You say, okay, you didn't do anything. I mean, I guess you reordered stuff, and well, you factor out a common factor, but how does that really help? Well, look at that thing right there, and compare it to that right there. This is our original problem. It's y double prime plus py prime plus qy with y1 plugged in. But y1 is a solution, right? That's our beginning assumption. y1 is a solution of this problem. So, because y1 is a solution to this problem, it satisfies the condition that if you plug it in, you get 0. So right here, this is 0. And of course, anything times 0 is 0. So that all just goes away. And in fact, I should probably write there, right? 0, since y1 is a solution. Okay, but if that's 0, all that's really left is this plus this equals 0. Okay, so we're left with u double prime y1 plus u prime times 2y1 prime plus py1 equals 0. And the first part, all of these terms are gone away. They're 0. All right, but now with this, let's do a simple little substitution. Let me take u prime and call it something a little more basic. Let me call it, let's use w since I'm already using u. So here, let u prime equal to w. Well, then u double prime will equal to w prime, right? The derivative of u prime is u double prime. So if you took the derivative here, you got to take the derivative here. Okay, so then I can rewrite this problem in a slightly simpler fashion. This is now going to be w prime y1, plus w times 2y1 prime plus py1 is equal to 0. Which makes our problem now first order and separable with respect to w. If you don't see that it's separable, let's go ahead and highlight that. When I was a student, I remember seeing this for the first time and going, what on earth are you talking about? And then it makes sense afterwards. So here we say, okay, I'm going to go ahead and, first of all, let's highlight that it's separable by actually separating it. Let me begin by simplifying. I'm going to divide everything by w prime y1. Same thing over here, w prime y1. Same thing here, w prime y1. When I divide that out, here I'm just left with, actually, no. My apologies. I don't want to get rid of the w prime, just the w. Sorry about that. That should be wy1. Because basically I want to get rid of this factor and this factor. I want to get rid of one from each. So if I divide by wy1, that's going to divide this away. Over here, this w is going to divide this away. And here, nothing actually changes. So we're left with w prime over w plus 2y1 prime plus py1. Well, actually, I guess I could just divide this as it is. So 2y1 prime over y1, I'll leave that as it is. But then here, if I divide these, the y1s just divide out. So I'm just left with plus p. And then over here, dividing 0 by anything is just going to leave it as 0. But now notice, I just integrate everything now. here. This is going to be, I'm going to move p over to the other side. I'm going to say this is minus p. And then over here I've got the remaining terms here. And I'm just going to integrate everything with respect to x. Integrate everything with respect to x. Integrate everything with respect to x. I've separated everything. Right? This is in terms of the different functions. Here, w prime dx, if you think back to Cal 1, this is just the derivative of w times the differential of the variable of w. That's just the differential of w. That's dw. Likewise here, this is dy1. So here I can get this to be integral dw over w, which we know that one. Here we have a constant 2, which you can just factor out. Integral dy1 over y1. And over here, I've got a negative, which that's technically a constant. I'll factor that out. Integral of p dx like this. And now all that's integrable. Here I can write this as natural log of absolute value w plus double the natural log absolute value y1 equals, and then here I'm just going to leave that as it is, minus integral p dx. We do have constants of integration happening here and here, so there should be a plus c on this side. For reasons that you'll see in just a moment, it'll be easier if I take that constant and move it to the other side. It is a constant, so I can just add or subtract it to wherever I need it. But what I'm going to do is I'm going to write it as plus c1 over here. Technically, it comes from these two, but it's just a constant. I can move it wherever I need to. All right, so now I do have a nice property of logarithms that says powers can be brought up, coefficients can be brought up as powers. So this is y1 squared. And then since I'm summing two logarithms, I can multiply their arguments. So this gives me natural log of absolute value wy1 squared is equal to, and then over here I'm going to leave that alone for now. Okay. So now let's see, I'm trying to isolate, what am I doing here? I'm trying to isolate my function. Yeah, I'm trying to find what u is, right? That's my starting problem over here. I want to find that coefficient function that will tell me how y1 relates to y2. And I don't have a u here, but u is buried inside of w. So I'm trying to isolate this one. For a moment, I lost track of what I was doing. So here, to get rid of everything around the w, I want to exponentiate like this. That's gone. And I'm left with w times y1 squared equals, let's see, there's not really much I can do to simplify here. Right here, since I'm adding a constant, remember that's going to be like saying this is e to the minus integral p dx times e to the c1. When you multiply two things, the powers add. But then this is just a constant raised to a constant. That's a constant. And in this course, I've been using the habit of calling that coefficient m instead of c. If it's ever plus or minus, I call it c. If it's ever multiplied or divided, I call it m. So here I'm going to write this as m times e to the minus integral p dx, like that. Okay. And so to get the w by itself, I can just divide that to the other side, giving me w is equal to m e to the negative integral of p dx over y1 squared. Keeping in mind that w is in fact u prime. Here I can replace that with u prime equals m e to the minus integral p dx over y1 squared, like that. And so to get the u that I was looking for at the beginning, I need to get rid of the derivative, and the only way to get rid of a derivative is with an antiderivative. So here the u that I'm looking for is going to be the antiderivative of this. Notice this is the antiderivative of something that involves an antiderivative, so we're going to have that happen twice. Here m is just a constant. We don't know what it is, but it's a constant. We can pull it out. So here we end up with m integral e to the minus integral p dx over y1 squared with respect to x. Plus a constant of integration, of course, since we did just take an antiderivative. This is the second constant we've seen, so I'll call it C2, like so. So what that tells us, since we now know what U is, what it tells us is if you know the solution y1, then multiplying y1 times this will tell you what the y2 is. It'll give you the other solution. So one solution can give you the second one as long as you multiply by this. Now notice that this is an arbitrary constant and this is an arbitrary constant. Okay, so what? So technically it works no matter what these constants are. Like if I put a 5 there and a -6 there, that'll actually work. Like I'll get a solution. y1 multiplied by 5 times this plus 6 will give me another solution that is part of the fundamental solution set. I can actually choose any constants. They're arbitrary, and there's nothing in here that tells me what they should be. They're completely arbitrary. So because they're completely arbitrary, we might as well be nice to ourselves and pick the simplest thing possible. Here, by convention, and nothing tells us we're supposed to do this, but I mean, come on, it'll make things easier. By convention, we set m equal to 1 and c2 equal to 0. So here we get, or at least what we generally will end up using is this version. U equals the integral e to the minus integral p dx over y1 squared. I was going to say plus something, but that would be 0. So just like that. Thus, y2 is equal to this times y1. A lot of times the y1 is written in the front. So we write y1 times integral e to the minus integral p dx over y1 squared. This is what we call the reduction of order technique. The name comes from the fact that right here in this substitution, we reduce it from a second order problem to a first order problem and then solve via separation of variables. You don't have to really worry about that. This result is what we need. So let's go ahead and write this out as a technique. This is the result, and this is the main body of our technique. So technique to solve something that looks like y double prime plus p of x times y prime plus q of x times y equals 0. Okay, so here you do have to have this be just one y double prime. If it's not, you can divide out by whatever's here so that you get one y double prime. And this does have to equal to 0. You do have to have a homogeneous ODE, and this does have to be second order, right? So the conditions, that's got to be a 1, that's got to be second order, and that's got to be 0. Assuming you have that, to solve this, given one solution, y1, first of all, we're going to go ahead and find u, which is given by the integral of e to the negative integral of p of x dx, where p of x is this coefficient function here, divided by y1 squared dx. Second of all, we're going to go ahead and multiply to get y2 by multiplying y1 times our u, what we find here. And finally, number 3, since you now have one solution given and one solution found, you have two fundamental solutions to a second order problem. The general solution will be their combination. C1 times the given y1 plus C2 times the found y2. And there we go. So let's take a look at an example of this to find the general solution of a problem here. All right, so let's go ahead and find the general solution of, let's do x squared y double prime minus 3xy prime plus 5y equals to 0. Okay. For this technique to work, we do have to know one of the two solutions. We do have to know one solution, so we're going to be given. And you say, well, is that always going to be given? No. In coming sections, we're going to show you how to find your own first solution, and then reduction of order gives you the second one. But for now, we'll give you y1 equals, and this is a kind of an intimidating looking one, but it is what it is. It's going to be x squared cosine of the natural log of x. Okay, at least on the interval, keep in mind this is not defined for 0. So since you need your function to be defined on a continuous interval, we're going to take the right interval, right? We're going to take from 0 to infinity. On 0 to infinity. Okay. All right, so here we go. First of all, this is not of the correct form. It has to be y double prime, nothing else. So the very first thing you're going to do is you're going to divide everything by x squared. If this is already 1y double prime, then you're fine, leave it alone. But since it's not, we're going to have to divide away the x squared. So our standard form is going to be y double prime minus 3 over x. All right, we're going to cancel one of those x's there. Y prime plus 5 over x squared y equals 0. And this is what we're interested in right here. This is going to be our p of x. Note that your p of x, it does include whatever sign is here. If this is a positive or if this is a negative, makes a difference. So this right here is p of x. Okay. So now we simply pop that in right there and then go through the long and arduous task of integration. Depending on the problem, this might be very simple to integrate once and twice. It might be challenging to do the first one and easy to do the second one, or vice versa. It really depends on the problem, but it really is just integration. So here we go. We're going to take u, and that's going to be the integral of e to the minus the integral of p of x is negative 3 over x dx over your original y1, which is going to be x squared cosine of the natural log of x quantity squared dx. Okay, so let's see here. All right, double negative makes that a plus, so let's start by simplifying that a little bit. That's going to be e integral of, the 3 is a constant, which I can just factor out, and that'll be 3 times 1 over x dx. And then here, squaring the x squared gives me x to the 4th, and then squaring the cosine of something gives me the cosine squared of that something. The natural logarithm is an argument. It doesn't get squared, just the cosine. Okay. All right, well, I know this integral nice and easy. That's just natural log of x. And since there's a coefficient in front of the natural log of x, I can take that natural log of x and put the 3 on as a power. So here, this will give me, oh, this one actually will be fairly nice. We end up with e to the natural log of x cubed, right, x cubed, right, over x to the 4th cosine squared of the natural log of x. Some of you may be looking at that and going, what happened to the constant of integration? Integral of the 1 over x is natural log of x plus c, right? In fact, you see I almost wrote that there as well. But remember, we have arbitrary constants in this problem. We have the m and the c, and this is another arbitrary constant, another plus c. But remember, this u is going to work no matter what version of it we use. So since our arbitrary constant is arbitrary, we're free to choose whatever we like. We don't want an infinite number of u's. We don't need an infinite number of u's. We need a single u to multiply by that single y1 to get our single y2. So here, we could put plus 1, or plus 12, or plus 50, or plus whatever we like. But since we can use whatever we like, I'm going to go with 0. Make my life a little easier. So here I end up with e to the natural log of x cubed, which the way exponentials and logarithms work, I just get x cubed. But now x cubed over x to the 4th, that's just going to give me 1 over x. So I end up with 1 over x cosine squared of the natural log of x dx. Okay. All right, so now we need to integrate that thing there. That one looks a little challenging. If you actually want to try it, you might pause the video here for a second and see if you can do it. Okay, so if you paused it and got it right, or if not, let's go and see what it looks like. Here, this is a substitution. It's a u substitution here. I'm going to take u to be the natural log of x. Here du will be 1 over x dx, but that's what this is, 1 over x dx. So here I end up with the integral of my 1 over x dx, that's a du. And then I've just got cosine squared of u now. But remember, cosine squared isn't actually cosine squared. It's 1 over cosine squared, which is secant squared. So this is integral of secant squared of u du. Oh, and I know that one. That's tangent. So here I get tangent, right? Derivative of tangent is secant squared. So antiderivative of secant squared is tangent of u. Again, plus a constant of integration, we're going to leave that off. Anytime we do this reduction of order step where we're finding u, any plus c's, ignore them. We're basically saying, well, any c will work, so we're just going to choose 0 every time. Can I choose a different number? Sure, you're welcome to make your life more complicated if you like. And then here, u is equal to natural log of x, which you can plug back in. So here we end up with the tangent of the natural log of x. And there we go. So that's going to be our u. Okay, so we took our first step. And of course, that is generally going to be the hardest one. The second step is just a simple multiplication. Okay, so now that you know your u, you can find your y2 by taking that u that you just found and multiplying it times the original y1. Okay, well, let's see. The u is tangent of the natural log of x. And then our y1 was x squared cosine of the natural log of x. Looks like that. Okay. But here, these are 3 different factors that are being multiplied, this times this times this, and multiplication is commutative. I can change this to whatever order I like, and I want to put the x squared in the front. Over here, I've got tangent of the natural log of x times cosine of the natural log of x, and tangent times cosine is going to give me sine of this argument. So here I end up with x squared. Remember, tangent is sine over cosine. The cosine cancels that cosine, and I'm left with sine of natural log of x. So here I find the second element of a fundamental solution set. And so now we found our y2, and now we're almost done. We found our second fundamental, the second element of our fundamental solution set. So now we're just about done here. So our fundamental solution set is we had been given x squared cosine of the natural log of x, and we ourselves found x squared sine of the natural log of x, and based off of our theorems from the last section, the general solution is to the linear combination of those. The general solution will be y equals c1 times x squared cosine natural log of x plus c2 x squared sine of the natural log of x. So given one solution, we can find the general solution. Oh, I should mention, of course, since our original statement was only on 0 to infinity, likewise here, this is only on 0 to infinity. And there we go. So that is it for this topic, and that's it for this section. If you have any questions, comments, problems, please let me know. Otherwise, I hope you all have a nice day.